Hello, everyone. Welcome to the next lecture on our lecture series on GANs. As today, we will be talking about deep convolutional GANs, or DCGAN in short. So, DCGAN is a landmark in the development of GANs, uh, which uh, which firstly proposed the use of convolution layers, transpose convolution, based on normalization in the training of GANs, which actually helped GANs generate very high quality images and also stabilize the training process a bit. So DCGAN actually laid the foundation of whatever advancements we have seen in GANs. And because of this only, like we started seeing that there is a lot of capability that generative AI can actually provide. Okay, so it is a very important method. So let's see what this is and what are the innovations that DCGAN has added as compared to the traditional GAN. Okay, so I will be very simple in my slides. I will also be giving you exposure to coding. So let's see. As I'm saying in every lecture, so we have an AI community, which is named Think AI, and we regularly share information related to AI in our WhatsApp channel. You can join this WhatsApp channel. We post lectures on our YouTube channel, and we are also on other social media channels if you want to join. Students have achieved remarkable performance in several domains, higher studies, competitive exams, research papers, and so on. Right. So there are so many success stories. And if you also want to have your name in this storyboard, so please join our community. It's totally free of cost. Like we have several mentors who are helping students achieve remarkable performance in the field of AI. Okay, so in this lecture series, this is the fourth lecture. So we have, like in the last three lectures, we have seen introduction to GANs, the evolution and the training of GANs, and some of the challenges in training GANs. Today we will be talking about like highly innovative DCGAN, which actually, like you can say, is the started, uh, uh, like in some sense, to my belief, it started the field of generative AI, and people started believing that there is a lot of potential in generative AI. So this started the field of generative AI. I mean to say in terms of the performance, because generative AI actually exists from like from many decades, right? But the quality content that GAN actually generated has actually changed the perspective, all right? How we actually see the generative AI, okay? And then we'll see about pix-to-pix cycle GAN and so on. In this lecture, we will recap GAN architecture. We'll see DC GAN architecture. We'll see about transpose convolution. Okay, so this is I think, very new technology for you. I think you know it from some other name, which is actually uh, like a like I think wrong pronounced name of the transpose convolution. And then we'll see how arithmetic operations are supported in GANs, and then we'll do some coding. Okay. So like how we evolved beyond the basic GANs. So there are several things that we actually see in the normal GANs, which is like one of the common problem is mode collapse. The basic GAN often fail to generate diverse samples, focusing on limited patterns. Okay, so it actually so the GANs actually generate same type of data. So that means only a few modes. It is not able to generalize on the different modes of the distribution. The training is actually unstable. To balance the training between the generator and the discriminator is actually very challenging, which leads to unstable conversions. And these actually use fully connected layers. All the GAN architectures prior to DCGAN relied on the fully connected layers, which were not ideal for handling images due to lack of spatial structure. Okay, so as you know that like we actually evolved from fully connected layers to convolution layers because of this spatial structure. So let's see like what is the motivation for using convolution GANs or the convolution layers in the GANs. So researchers realized that leveraging convolution layers could enhance GANs performance for image generation by better capturing the spatial hierarchies. As I said, this spatial hierarchy is the like most of the like important thing from which we move from fully connected layers to the convolution layers. So the same motivation actually led the researchers to see like using convolution layers in the GANs as well. Okay, so we'll see how this is actually done. Okay. Okay. So let's see about DCGAN. So here, like these are the a few of the images like that we can see from the original GAN on the CFAR dataset and the DCGAN on the bedroom dataset. So you can say that these are the randomly generated bedroom images, show slightly odd but almost realistic bedrooms. Okay, here the images that are generated are not even uh, like understandable. Like so, for example, you can see that there is a bird kind of structure, but you don't know what it is, right? There is a line kind of thing, but you don't know what it is, right? So the images are generated, some kind of special information was trying to be captured, but it is not very clear. But see the DC GAN, right? There is like a few drawbacks here. For example, this particular image where there is a door and there is a bedroom, but you can see, right, all of the components in the images are understanding, right? You can see, okay, yes, this is a bed, this is a window, this is a door, and so on, right? These are very high quality images that the DCGAN has actually generated. Okay, this is the original paper that was proposed by the researchers for DCGAN. You can see this for more details. Now we will see how this architecture actually came into existence, how this is trained, and how you can code it. Okay, we'll see it. Like we'll go step by step, very slowly, and I will focus more on the fundamental things so that you understand how the GANs actually evolved. And let's just go into the technicalities. More examples where DCGAN actually generated hotel room images. You can see that this is coming out to be more accurate as compared to the images that we have seen in the earlier sessions. Okay, now I think I have already told you why we are moving from fully connected layers to the convolution layers. But let's just see some more emphasis here. And the problems with the fully connected layers is that the basic GANs uses fully connected layers, which results in output that lacks spatial coherence and which is necessary for generating images, or you can say quality images. Okay, so now let's see about convolution layers. You must be knowing about convolution neural networks. These are the convolution layers who were very successful in CNNs for image classification, where we adapted like GANs, where these are adapted in the GANs as well to better model the spatial information in the images. Okay, so the convolution GANs could now better handle image structures, allowing for more detailed and realistic outputs. Okay, so now this is the first attempt where the early modification to GANs introduced convolution layers but did not establish a standard architecture. Okay, so let's just see about DCGAN. Okay, so now the DCGAN paper came in 2015 in I'm not sure. I think in NeurIPS, but I'm not sure. You have to check. This came in 2015. And DC game aim to stabilize GAN training and improve the output quality by using the fully convolution neural networks for both the generators and the discriminators. Okay, now you must be seeing that generator is actually generating the image. It is okay from some noise to image. Okay, is there, and discriminator. Okay, so it is doing some kind of classification between the real and the fake sample. I think using convolution layers in the discriminator make more sense, but in the generator, you need to generate a like an image from a low dimensional information. So you must be wondering how we can do that. Okay, so let's just see. I will tell you about all the technicalities here. The impact that so it was found that it is a landmark development in the GANs, and it establishes a framework for robust and high quality image generation. Okay, so basically the contributions that they have done is the standardized architectural elements like started convolution they have proposed for the generator, and the batch normalization to stabilize the training and enhance the gradient flow. Okay, so let's just see what all these things are. So this is a very important slide. If we are talking about DCGANs, I think why I'm saying an important slide, because I also have an exam at the end of this lecture. So you may actually want to answer that exam, and like you may want to comment on this video and see like what all these things are. Right? Let's say if I find that the comments are actually very good, I may like may name you in my next video. Okay, so this is I think what I can do. So it doesn't use fully connected layers, remove fully connected layers lying instead of the convolution layers to better capture the spatial hierarchies. Okay, so now there are two things: convolution layers and the transpose convolution layers. Okay, the generator uses transpose convolution to progressively upscale the random noise to a full resolution image. Okay, whereas the discriminator uses tided convolution to downsample the input image, distinguishes the real from the generated data. Okay, so the discriminator, what it is doing is it is downsampling the image. So for example, like we have a full image and we are downsampling it to the like you can say to more features of the image, and then we can have some understanding whether it's a real or the fake image. Okay, but the generator actually uses transpose convolution, which progressively upscales the noise to an image. Okay, so that means the random noise we are actually making it into some understandable structure, and we are upscaling based on the transpose convolution. So that means we have some structural understanding, and then we are building some structure on the images. Okay, it also uses another innovation as batch normalization, which is applied to both the generator and the discriminator, which helps to stabilize the training by normalizing activations, reducing issues like mode collapse. Okay, I am sure that most of you know about batch normalization. If you don't know, I think in my slides I will be talking in brief about it. But if you have queries, I think I have explained this in detail on my Quora post. You can check that, or maybe you can comment it and I can share some references. Okay, it uses leaky ReLU and the discriminator and 10H activation in the generator. So basically they have experimented, and they have seen that they provide more improved gradient flow, and it actually stabilizes that training. Okay, so these are the two modification in the generator and the discriminator as well. But these are the two major modifications, you can say. So this one and this one, right? These are the two major modifications which actually gave the better quality input in the DC GANs. Okay, so now let's just see about the generator in the DC GANs. Generator upsamples. So just please remember that it upsamples the size of the image into multiple stages. So this is our Z. Okay, so it has let's say some dimension, let's say 100. Okay, so it's a very small image, a very small size. Now what we need to do is we need to have some structural understanding. We need to upsample it. Okay, so we are going from low to higher, right? You can see, right? So this is from 100 to, you can say, 4 cross 4 cross 124, and then it goes to 8 cross 8 cross 512, and then so on. Okay, so now we have more like upsampling across the like higher layers in the generator. Okay, so this is the GZ. Okay, so how it is doing is it is actually based on the lesson scene modeling. So a 100-dimensional uniform distribution Z is projected to a small spatial extent convolution representation with many feature maps. Okay, so I will tell you what it is: a series of 4 fractionally stated convolution. Okay, in some recent paper, this is wrongly called as deconvolution as well. Okay, but this is wrong. Okay, you can, in the loose terms, you can say this is a deconvolution, but if you want to name it technically, so then it is called as fractionally stated convolution or the transposed convolution. Okay, so then this is actually converted into a high level representation into a 64 cross 64 image. Okay, this Z, the image of 100 dimension was actually projected into this particular 64 cross 64 dimension image. Okay, so this is what the transpose convolution is. It is actually upscaling every time. I will tell you how the mathematical operations are actually working, but I just want to give you some intuition like what the generator is actually doing, and then we will go into the mathematical part as well. Okay, so notably, no fully connected layers or pooling layers are used here. Okay, only the upsampling layers or the transpose convolution layers are used here. Okay, so now let's just see what is transpose convolution. It can be used to upsample, like I'm repeating again and again, like please remember upscaling, because generator is actually upsampling the lower dimensional in random noise to a higher dimensional in image. Okay, so it is upsampling a tensor or the image to a higher dimension. Okay, so it is also known as fractionally strided convolution, or improperly many people call it deconvolution. Okay, but it is transpose convolution. Better you call it transpose convolution or fractionally strided convolution. Okay, remember how the convolution operator actually works in the matrix multiplication. Let's say if this is the convolution operator between x and f, what we do is in the vectorized representation, how we do it, we convert this f into a matrix representation, let's say a of f, and the vector representation of x, then this is a dot product. Okay, and this dot product actually gives the output of the convolution operation. Okay, so let's say if I say about the transpose of this convolution, what we will do is we will do the same operation. What we will do is this matrix that we have here, we just compute the transpose of it, and then we do the same operation. Okay, so basically the same thing is happening, the same dot product is happening here between the vector x, but the matrix is actually transposed here. The same operation is this. That's why it is called as transpose convolution. Okay, you might be seeing that okay, mathematically it's simple, but what is the intuition how this is working? I will tell you with an example, but see that this is how the convolution actually works, and this is how the transpose convolution is actually working. Let's just see an example. Okay, so I will first tell you about the convolution operator. Here I assume that you guys know about the convolution layers in the CNNs. Okay, so this is the convolution operation in the CNNs. Okay, what happens is that say this is your input image 4 cross 4, this is the kernel 3 cross 3. What it will do is it will be applied here first. This kernel is applied here. Okay, so when you do multiply it with this, it will generate a number 84. Okay, I hope I'm not doing a mistake. 3 plus 6 plus 12. 3 plus 6 is 9 plus 12 is 21 plus 7 is 28 plus 4 is 32 plus 9 is 41 plus 7 is 48 plus 4 is 52 plus and 32. 32 plus 52 is 84. Yes, that's correct. Okay, so this is the like element wise multiplication of this kernel and this particular window, and then this is the 84 value we are getting, and then we will slide over this this kernel on the window, and then this is the I think the next window that we will be coming up with, and then we are getting the next value. Okay, so this is how the convolution operation is actually working. I hope you all know about it. If you don't know, please comment. Don't hesitate. I will give you an explanation in the comments. Okay, or I will share the proper references. Okay, so then you will get the same value and then so on. Okay, so this is how the convolution actually happens. But in the computer, what happens is we create a convolution matrix. Okay, as I told you in the previous slide, we like to perform this convolution operator, we convert the kernel into a matrix, and then we do the dot product with the with our input. Okay, so what we will do is we'll convert this kernel into a convolution matrix, and then we'll multiply it with the input in a dot product. Okay, so that means this actually is transformed into a convolution matrix. Okay, so you can say this is a filter F. Okay, and we are going to A of F. Okay, so this is A of F. Okay, so what is happening is we are actually opening it 1240. This is the first 1130. Okay, and 1240, and then there is nothing in the fourth one. Okay, and then what we will do is we'll do shift by one. Okay, so 0 is here, 0 1 2 3 4, 0 1 1 3, and so on. Okay, and then we'll shift it by 2. Okay, here we can't shift. So this is actually shifted to the new, uh, like you can say the row 1, 2, 3, 4, and the all zeros are here and so on, right? So we'll keep on shifting it, and this is the matrix that we are actually coming up. Okay, so this is the AF we have, and then when we do the dot product with this particular input, we'll get the same output. Okay, this is how the convolution operation is actually working when we have this convolution matrix. Okay, so now let's see how the transpose convolution actually works. Okay, so this is the transpose version of the same matrix. This is 4 cross 16. We have converted into 16 cross 4, and the input is this. Now the input will be this. Okay, 2 cross 2. It will be, I think the numbers are actually wrong here. It should be 84. Oh, sorry. What is happening? Okay, it should be 84. Okay, 84, 84, 87, and this should be 87. Okay, I think you understand it now. So it should be 84, 87, and 60. And then this is the output that we are getting. And then we will do the transpose here. Sorry, we'll convert into 16 cross 1, will convert into 4 cross 4. Then this is the output we are getting. Okay. Okay, so we should get the same matrix. I think this need not be 84, 87. If you convert that to the same uh, like values, I think you will get some values. There will be some image as output. Okay, this need not be 84, 87. Okay, I'm sorry for it. This is, let's say, 2 3 4 or 1 3. Sorry, this is whatever the value are. You can see. Let me just see where the eraser is. Okay, so this is the actual values. Okay. Okay. So this is actually this. This should be 2 3 and 4 3. Okay, so this is the change. Okay, other things are same. I think the values are actually generated based on this metric, not on the earlier metric. So this is the same, and this is the output you will get. And then when you make a transpose of it, it will can generate a 4 cross 4 image. Okay, so this is how the transpose convolution actually works, or the fractionally strided convolution. Okay, this is an important slide. I will ask a question on it. Okay. Okay, so let's just see. Transpose convolution can be equivalent to a simple convolution with zero rows or columns added zeros to simulate fractional strided convolution. Okay, this is the original input. This is a zero padded input. And let's say we'll do the kernel multiplication or the convolution with it. Then this is the output that you will be receiving. Okay. Okay, so both can be equivalent if we actually do this, add zeros to simulate the fractionally static. Okay, so this is how the things are actually working. This is the original input. We actually add zeros in between, and then we'll get the same output. Okay, so another innovation that DCGAN actually adds is the batch normalization. It dynamically normalizes each feature to have zero mean and the unit variance. Okay, it is applied to on each layer. It is applied to each layer after every update, and input is the mini batch of let's say of data xt at let's say iteration t. We compute the mean and standard deviation of every feature. Okay, at that time, and then we normalize that feature using this particular value. Okay, so this is how things are actually happening. And if you want to see the more details, like you can go to this particular paper, and basically these are actually computed like there is a another meaning of these like mean and standard deviation. I think when you go into the details of batch normalization, I think you will get to know. But I think let's just don't confuse yourself, and have only these meanings only, a mean and standard deviation. And this is how we are normalizing each feature in the like, or maybe you can say each layer of the neural network. Okay. Okay, so how this thing is actually happening, how the batch normalization is actually normalizing uh, the values at each layer, like as a running average of the mean and variance. So what it actually do is this is how it actually updates the mu and sigma at every time step. And so these are the hyperparameters that are learned. Okay, so this lambda, there is a significance of lambda, like we can see that, but so this is only applied in the training side. When like we do model.eval, the batch normalization is actually turned off and it is not applied. Okay. Okay, and it also like batch normalization is actually found to stabilize the training and also reduces the training time and produces better results, not only in the GANs but in the general neural network setup as well. The batch normalization actually helps a lot. So because it helps to reduce the internal covariate shift that we see in the data between the layers. So when this is actually reduced, the neural networks actually perform way better. Okay, so now another thing is the vector arithmetic in the DCGAN. So this paper, the DCGAN paper also proposes a vector arithmetic between the images. So for example, let's say we have an image of a smiling woman. We do the negation with the neutral woman and then we add a neutral man. So the output that comes out to is a smiling man. Okay, so that means these are the images you have given as the input and some arithmetic, and this is the output that you are receiving. Okay, how this is done, we'll see, but this is the example that they have given in the paper. So I just wanted to show you. So the advantages of DC GAN over the conventional GAN is that it improves the image quality. Like the output quality in the DC GAN is way better than the traditional GANs. The training is more stable. They have proposed a standardized architecture. Right, how the convolution, studied convolution, or the transpose convolution are actually used. Maybe you can say studied convolution and fractionally studied convolution are used in the GAN architecture, and there is a formal or the standard architecture that this paper has actually proposed. Okay, and there is a versatility of extension. So DCGAN actually propose a base for the GANs, that okay, so it can actually generate a very high quality images, and then it also laid the foundation for the future advancement as well. So the later all the GAN models that actually came were based on the DC GAN only. Okay, so so DC GAN actually produce high quality images compared to the previous GANs and sets a new standard. And so this actually inspired the further developments in GAN. For example, conditional GAN were developed based on this, progressive GAN, style GAN, cycle GAN, pix to pix GAN. We'll also see these in the next uh, lecture. And they actually did very good in the image translation as well and the super resolution as well. Okay, so there is a widespread application of DC GAN for the creative application, scientific research, and industries like fashion and media. There is a lot of use of GANs in fashion and media. So I would suggest to explore GANs and see like how you can actually do very good things in the GANs. Okay, if you want to see more details about DC GAN and how the training are actually coming up, and if you want to go with the code and more hacks to see the GANs, I think you can actually go to these particular resources. Okay, sorry for it. This is the GAN DC GAN tutorial, and these were the like more common like solutions for the issues that you are coming up with the GAN training. Okay, so this is the exam. Maybe before the exam, I would like to go with the coding, and then I will leave you with the exam. Okay, so let's just go to the coding part. Okay, so this is the, okay, sorry. I think this is actually taking a lot of time. This is a like notebook that I have created from several parts on the internet. I don't claim that it's my notebook. Okay, so but I think I've tried to collate information from different sources, and like I think I will share this notebook with you, and you can actually see like how to actually use a first GAN model. I think I have given all the details of the GAN at the beginning. This detail was also copied from some resource on the web. So I don't claim any authorship here, but I am actually giving the information which is available on the web. Okay, so here I am importing the necessary libraries. I think you can go into the details. Okay, so we are actually using MNIST dataset. We'll try to produce, I think in this particular example, we'll produce the numbers from the MNIST dataset. And then I also have another example where you can produce the realistic faces. Okay, so this is also another example I have. But let me just give you a very fair example on the MNIST dataset so that we can actually see how to generate the faces as well. Okay. Uh, Okay, so this is how we are loading it, and this is the okay. So as I said, the generator actually uses transpose convolution. So here you can say that I hope you know how to use Keras. So I will be going like with the faster pace here. So what you can do is like I will do add a dense layer initially, and then I'll add batch normalization and then leaky ReLU, and then I have added 2D transpose convolution. Okay, every layer with the batch normalization and leaky ReLU, and this is how the generator model is actually coming up. Okay, you can add more transpose convolution layers based on like what size you want. Okay, so this is how like the normal you can say the CNN architecture was actually made. So the same way you can made a generator as well. Okay, similarly, I think this is how we are actually setting up the generator, creating an object of it, and we are initializing it, and then there is a discriminator. It is very simple. Here we are only using convolution layers and the leaky ReLU. Okay, and then output is only one node where we are saying a probability of whether it's a fake data or the real data. We create an object of it, and like we set the binary cross entropy as our loss function, and we take the loss of the discriminator and the generator, and then we set the optimizer of both as Adam, and then uh, we set the checkpoints, like how to set the checkpoints, and we set the data and all those things, and then we do the training loop in this training step. Okay, so what we do is we generate the real output, fake output, and then we first what we do is we like compute the loss from the generator and the discriminator, and then we continue the training part. Okay, so this is one step, but actually this is how the things are actually working. So this is the training step for each image batch in the dataset. We are doing this training step that is actually held in this particular function, and then we continue the training part. Okay, so I think for me it actually disconnected. Now it has connected again, but this is the output that you will get after a few epochs. Okay, so this is after 24 epochs, but let's say if you train it for, let's say, 50 epochs, the output quality will be more accurate. Okay, so I will tell you, I think I have a GIF. Okay, this GIF is actually is now out of memory, but I would have shown like how the training actually evolved. Okay, so this will actually create a GIF where you can actually see how the data actually evolved with the improvement in the training. Okay, so this is another notebook that I have collated from several sources where we can actually generate the faces. Okay, I think the data set that we have used is the Celeba dataset, which actually can create celebrity, have celebrity faces. And this is the dataset. And I think, let me just see if I have some output here. Okay, so this is also, I actually stopped in between. The same thing is actually happening here, and the same kind of setup is there. Okay, so I think this is actually, I commented intentionally because I was taking a lecture in some university and I wanted the students to do their work and create their own network. Okay, so this is how you create the transpose convolution here in the generator, and the normal 2D convolution you are using in the discriminator. Okay, and then the training will actually go the same, and this is how the GAN architecture is actually, DCGAN is actually working. I actually leave everything on you. If you guys ask me on comments that like how things are actually there, if I can share this notebook, I will do that. Otherwise, I'm sharing it on my web page and you can access it from there. Okay. Okay, so this was the small coding part. I've given you only the intuition part, but I think like you can make sense from it, how the generator and the discriminator is actually doing the things. So if you have any queries, you can ask me in comments. And this is the exam that I can actually like give you, and you just see like how much you have grabbed from my lecture, and you may want to actually answer this particular exam. Okay, so join this community, as I've said, if you want to learn more things about AI. Okay, so thank you. See you in the fifth lecture on paired image to image translation, which is pics to pics. Okay, thank you. Okay, this is the exam that I would like to highlight again. So please do attend it. Thank you.